Good afternoon, everyone. I think there's at least 2 people here. Yeah. Cool. I was waiting for this plane to go by. So today I wanted to talk about this STEWART platform I've been developing. I have all the parts here next to me, all chilling. We're going to assemble that, but first I want to talk a little bit about the design itself, as well as some of the examples, its history, where it came from, where you might recognize it. So, a STEWART platform is a way to develop a 6 degree of motion simulator. It's often used for simulator, but can be used for lots of stuff. But you can see it can move in all 6 axes, so up, down, forward, back, left, right, and then also pivot on all 3 axes as well. And the unique thing about it is that just the way the math works out, there's a completely unique solution for every position of this top platform based on the length of these actuators. So very commonly, these type of systems are built on linear actuators, just like this. Really? Okay, there we go. So very often they're built on top of linear actuators, and using the right type of math, just some linear algebra, you can basically find, no matter where you want this top position to be, the length of all of these actuators. But we're not going to talk about the dynamics today. We're going to focus on actually building it, how I came up with the design, and some examples of where we might have seen it. So, very famously, the first STEWART platforms came from the first widespread use of STEWART platforms came from flight simulators, and very notably the Star Tours ride at Disney. So if we look up Star Tours at Disneyland, ride behind the scenes, you can see it's just a STEWART platform. You've got the 6 linear actuators, just like this system. And then there's been modifications and adjustments over time. You can kind of see it better here. 6 linear actuators, all controlling the vehicle you sit in. Yeah, and then these designs continue to be improved upon, and there's been other variations, like on Millennium Falcon, the Millennium Falcon ride, also at Disneyland. They actually use 8 actuators instead of 6. This increases the rigidity of the ride a little bit, so it's a lot more rigid, there's a lot less movement. But it does over-constrain the system, meaning there's even more ways to drive the actuators in such a way that you break it. Because you can imagine, like in this position of the ride vehicle here, if you were just to shorten one of these, that would be an invalid configuration of the actuators. It would be something that would damage the system if you tried to drive the actuators like that. So you have to do very specific math to calibrate how you drive these linear actuators and get all the correct positions for whatever movement you're trying to create. With the 8-axis system, with the 8 actuator system, it's even more intense because there's even more ways to mess that up. but it does provide a lot of rigidity. So if we go back to my design, we'll see that there's a lot of... I'm using 6 actuators because that's the minimum required in order to get that 6 degrees of freedom. And then one thing you'll notice if you look up like a STEWART platform, even like the Wikipedia article, a lot of the times they'll end up with these like hexagonal layouts where these two are next to each other and then there are 2 up here, and that again helps with rigidity. Not necessarily anything like it doesn't necessarily required for the kinematics, but it's helpful for the rigidity of the platform. Now, when I was designing this, I entirely forgot how that all works together. I just kind of forgot about that. I made them evenly spaced. The dynamics should all work the same. It might just be a little more floppy, wiggly. Yeah. So, since this is a live, feel free to ask any questions about what I'm working on now with this STEWART platform, or any questions about previous videos or projects I've done. I'll be happy to answer anything you guys want to know. So if we take a look at the individual actuators on this, it's a pretty simple rack and pinion setup. This is just a little 9-gram servo. If we take a look over here, it's just one of these little 9-gram servos. They're super small, but they should be plenty torquey because 6 of them will be working together for this actuator. And then I've got a pinion gear driving a rack, and this rack actually just sits in the carrier here with a little trapezoidal pattern so you can't pull it out from the side. And you can kind of see that here if I do this. This pattern's got the trapezoid, the holder has a trapezoidal slot, and they just fit together just like this. They slide in and slide out. Yeah, so I see Andrew Hill asked, is this for the dark ride? Yeah, so what I'm envisioning this for is actually an animatronic that's going to attach to the dark ride. One of the if you look back in my channel's history, I had a video called Making a Yabbit. A Yabbit was, actually I have him here. He was this silly little alien animatronic. He had some movement in his head. He flapped his wings. He wiggled his tail. He spit water, which was pretty cool. So what I actually want to do is I want to take this STEWART platform that I'm developing, and I want to make that the neck of this Yabbit so that he's super duper, he has lots of animation, so he can move his head in all the axes. Since his body doesn't move much, he'll be super, he can rely on that neck movement to convey a lot of emotion that otherwise wouldn't be possible. So, yeah, so it's a rack and pinion, it slides super well, and then because there's so much movement of that top platform, it basically needs to have some way that constrains it rigidly translationally, but still allows a lot of rotation. So I'm using a ball joint on either end of these actuators to allow the vehicle, to allow these platforms to be controlled by these actuators without having any issues rotationally like that. One issue with this is you can see a lot of these actuators are sliding around. are spinning around and the servos are actually colliding. I kind of expect this to be a problem once I actually build it. So you can see how it's kind of turning and colliding with the other ones. What might have been better is even if I used like a ball socket for the top and then used something like a U-joint at the bottom, that would have constrained the rotation in the yaw axis like this. That way it wouldn't spin like this, and I can force the servos to be facing the outside. Another option for a future revision is if I had them hexagonally, like in this animation of the stores platform, I could put a servo here in this gap, and then one in this gap, one in this gap here, one in this gap, so that there's more space for them to move around and not collide with each other. This would be like, and by that I mean put one actuator, so the holder and servos on the top, and then next to it I flip it so the holder and servos on the bottom. With all that being said, I think we should probably start working on the actual assembly here. So one thing about it is it's got pretty... I printed these with ASA, which I don't really like ASA all that much. My Ender 3 here really can't handle it, even with an enclosure I built out of cardboard. So they're pretty warpy and not the most dimensionally accurate parts I've ever made. So there is going to be a little bit of sanding involved to make it slide nicely in the holder. But then there's also going to be some slop. So in this one assembled one I have, there is slop. You can kind of see how much movement there is. If I bring that a little closer, how much movement there is there, which is only going to amplify, I think, with having all 6 of them. So maybe that's a case where using an 8 actuator design, like I was talking about earlier, could be really beneficial, because that could cancel out some of the slop because there's so much over-constrained motion. So I'm going to start just by sanding these a little bit, just to get them to fit nicely in their holders. And once we have all those sitting nicely in the holders, we can then go back and install the servos and the pinion gears. So it's not much sanding. Even that was almost enough right there. It's mostly just the elephant foots I'm getting. And if you don't know what elephant's foot is, it's when on that first layer of printing, the printer kind of is too close to the print bed and it like pushes out further than where it's meant to be. So you can kind of see it in like, looking for a good part to show you guys. It's probably going to be hard to see on camera, but you can kind of see it here. Let's see. You can kind of see how it comes out a little bit at the very bottom, and that's that lip I'm trying to sand off right now. I'm thinking I'm going to get some more aggressive sandpaper out, just to make this a little bit faster, because I don't really want to spend all day sanding these down. So we're pretty close with this one, I think. Ooh, I got it stuck. Maybe not too close then. that's feeling all right there. See how it's moving? It's moving all right. It's still a little bit sticky up here at the top, so I'm going to sand that a little bit more, and then I think we're good for this one part. Yeah, that seems pretty good. Okay, on to the next one. With this one, I think I saw how much sanding needed to be done to that last one, so I'm just going to start by doing a lot. Again, like I mentioned before, since this is a live stream, feel free to ask any questions about my previous projects on this channel, or anything you want to see in the future. Since I'm just sanding right now, now's a great time for me to answer questions. That one was super easy. That's sliding like butter already. Let me get the next one going. I'm seeing a few people bounce in and out. Just in case anyone wasn't here when I first started the stream, what I'm building here is a... here we go. I'm building a storage platform. A storage platform allows for 6 degrees of motion. So that's up, down, left, right, side to side, and all the rotational axes on this top platform using these 6 linear actuators. And what I plan to do is use this as the neck of an animatronic. Using this as a neck will allow super expressive motion and allow a lot of emotion to come through for the Yabbit animatronic that I've built on my channel. I'm rebuilding him with a more advanced mechanism, give him more emotion, give him a better animation. So I'll leave that up in the corner there. I'll move my camera a little bit so you guys can get a better view of what I'm working on here. So right now I'm sanding down the linear actuators, these rack gears. I'm sanding these down so they slide in their holders nicely. Oh, that one's feeling good already. And I'll move on to the next one. The point of these is to act as linear actuators when I eventually attach these 9-gram servos to them. And you see I have one of these already assembled. So as it moves in and out, the servo spins, and it works this other way. If the servo spins, it'll force it in or force it out, and that way it can control how far the linear actuator expands, and thus the movement of the storage platform. That one's feeling good. Yeah. Now last one, we'll get this is the last one we need to sand, and then we can get those linear actuators on board. This one feels pretty bad, but it looks like, it's close. I just need to sand a little more up here on top. There we go. That's feeling nice and smooth. Okay. So next up, we've built the rack and pinion gear and their holders. What's next, I believe, is going to be attaching the pinion gears to the servos. Now, a lot of people on the internet will say you have to use these servo horns when using a servo because a 3D print is never going to be strong enough or precise enough to hold these little servo arms. If we look really closely, which I'm not sure it's going to focus, there it goes. There's these little tiny grooves in the servo horn that mesh with the spines on the servo horn output here, on the servo output shaft. And those mesh really nicely. But those are way too fine for 3D printing. So what we're going to do instead is I actually just printed this hole a little bit too small out of some PETG filament, and then I'm just going to do a press fit, which will like basically carve those splines right into the gear. It's not perfect. With a servo any stronger than this, it would strip out pretty quick. But because these servos are so small and very low torque overall, the servo actually stalls well before the plastic strips off of that. So I think this will be just fine. I've used it in the past without any issue. Now, one thing I would be doing more ideally is I could have set it up so that I had like a servo tester or a microcontroller already ready to go with to set the motors to the final position, and that way I could set the gears with the right position corresponding to the potentiometer built into the servo. What I'm actually just going to do is I'm just going to hand turn the servo using one of the actual servo horns from the kit. And that is close enough, good enough for now. I'm sure I'll have to go back and calibrate it more properly later, but this is plenty good. And then I just want to push it on basically as straight as I can. Just straight up and down. So see, the push fit's not too bad. Just slides right on, and then I can move the servo. You can probably hear the servo spinning if I hold it close to the microphone. So we slide. Yep. And then I designed this holder with screw mounts just right for these servos. So it's super easy to install them. And like I said, this Storts platform here that I'm building, Storts platform, shown here in Onshape, is eventually going to end up inside of an animatronic Yabbit. And the first model of Yabbit here, this is V1, the original guy. up to show you guys the Yabbit. He was a lot less advanced. This was much earlier into my engineering career. He was built out of a cookie sheet that had cut up with tin snips and screwed together with self-tapping screws. The gears are just holes and paper clips. Not the gears, but the pivot points are holes and paper clips. No bearings, no precision. You see it's all super wobbly. A lot of popsicle sticks were used for mounting. Let me take you off the tripod so we can get a little bit closer. So you can see, like, in here, these were the tail actuators, so these went back and controlled the tail. These were mounted with popsicle sticks because these were a pretty far afterthought. I wasn't good at soldering yet, and I definitely didn't know about heat shrink. So for the resistors on the RGB LEDs and the eyes up here, that was just all hand soldered and then covered in electrical tape. And then the head itself was made out of baling wire and popsicle sticks. Apparently some, it looks like rubber bands and fishing line. So there's some real high quality engineering here. One thing I will say that I got right was these magnetic connectors for the back of the head here to snap the skin on nice and easy. That made it a lot easier to get inside, but still not the greatest. It's still pretty hard to get in there. As you can see, the whole front half is covered. Though, I think the face did come out pretty well. These eyelids are decent. The ears did give a wiggle, and it did spit water, so that was pretty cool. But for V2, if you imagine, we take the head of the Yabbit, we mount it onto one of these 6 degrees of freedom actuators, this STEWART platform that I'm building right now. It's going to have a lot more movement and a lot more freedom to display emotion. So you might imagine it can move its head up and down to be like happy, to give it like a, oh yay, I'm bouncing, I'm happy. Or it can shake its head, or it can throw its head all around. So this will give it a much more expressive action. And a STEWART platform is actually pretty similar to the neck of a human. In your neck, you actually have about 6 muscles that control your neck, just like these linear actuators, that pull down through here, and your vertebrae act as the support, so you can move your head forward and back like I am now. And that all comes from a design like a STEWART platform, biologically built into you. So going back to working on the linear actuators here, let me get a tiny screwdriver. I'm just going to mount this servo right here onto the adapter. This is the wrong screwdriver. One annoying part about these tiny little actuators is they are pretty finicky. They're small. Depending on where you order them from China, they don't work too great. Lots of failure rate, very high failure rate. But you do have to accept that it's what you're buying. I believe each of these do cost just under $2, so you really can't expect too much for electronic component at $2, much less a servo. So when it's all screwed down like this is actually a lot better than that first one here. This one I haven't tightened all the way, so there's still a little bit of slop in the servo here. This one I just tightened down all the way. And this pinion gear is actually holding the rack down. It's providing a little more friction, so it's a little bit harder to move, but it's a lot more rigid. There's a lot less slop once it's all tightened down, which is always a good sign. Just like that. So that's working great. Let us get on to the next few. And again, guys, feel free to ask any questions about my channel, about any future projects, anything I've done in the past, anything you would like to see. I'd love to hear your suggestions. Alright, let's get another gear out, another servo out. And just like before, I'm going to set the position of the servo pretty rough. I'll have to come back and fix that, but I'm not too worried. So as the servo spins this way, I want the servo out like this. Yep. It's just a nice press fit, nice and easy, right into the plastic of the pinion gear here. There we go. Seated pretty well. Spinning nicely. There we go. Cool. Where did the screw kit go? There we go. That one's feeling nice too. There we go. 3 down, 3 to go. Not too bad, not too bad. Ooh. The other thing about these Chinese servos is that this one sometimes they come like this. This is all greasy. So that's going to be fun to try to hold little screws when my fingers are all greasy now too. And they also have terrible quality management. You can see these stickers aren't even close to the center. And I have a feeling that's because they've shifted since I've had them, or in shipping, because it's so greasy, they're barely holding on there. I designed these actuators. So if we look at this one, I designed it so that the gear teeth, the pinion teeth, mesh exactly with the rack teeth. So you can see I got it so there's one tooth beyond the end of this pinion gear. And if we go in all the other way direction, there's one tooth at the end of this rack gear before the servo reaches its limits. And I did that so it's super easy to assemble, as well as minimizing the actual space of the actuator. So when I'm laying this in, all I have to do is I have to say this final gear on the pinion gear meshes with this first slot in the rack gear. If I had made this a full gear, it would be a lot harder to know exactly what tooth should mesh with what. Additionally, I designed it this way to give it a little more space during movement. So for the most part, it's going to sit right in the middle of its actuation. And at the middle, you can see none of the pinion gear, let me show you one of these, none of the pinion gear is sitting past this servo. So it minimizes the space used by the animatronic in the most common position. And then as it goes up, you can see it sticks out, but that's inevitable. And same with going down. It sticks out past the servo. But where it's going to be most of the time, it's clear, and it leads to minimal invasion of space. Oh. And another thing about them being all greasy is it makes these Ziplocs pretty hard to open. But got that going. Screw this one in too. Okay, there we go. And I dropped the screw. Okay. Another thing about this ASA material that's kind of got me stressing is my printer doesn't really get hot enough to print it. So there's a lot of imperfections in the print. If we get close enough, will it focus? You saw it. Let's see. Kinda? No. Regardless, these layer lines don't have the best connection. So as I'm screwing these screws, I'm hearing a lot of cracking. And I'm really worried I'm going to split the layer lines right down on the layer lines and split the part in half, which would be unideal for sure. So I messed that up. I was just talking about it too, but I got the pinion gear misaligned here. I misaligned it with the rack gear, so I'll have to take that off and redo it. That's good. Good start. Always a good start. But easy enough fix. That was super simple. There we go. Nice movement all the way through. This one is a little bit tight. I think it can be worn in a little bit though. Just as it moves, we'll wear in the plastic. It's just plastic, so it's not like the strongest thing in the world. Let's see. I want it so it has it spins this way. So I want it in this position. Just a nice press fit right on. This PTG is pretty soft, so it's pretty easy to do press fits like this. And then it'll slide out. Yep, there we go. And then screws. There we go. Nice movement. Oh. Come on. There we go. There we go. That's pretty nice. And the final one real quick. Moves nicely. Cool, cool. And screw balls. Cool. So that's all 6 assembled. Looking good. Cool. So all 300, not all 300, all 6 actuators built. The next step is attaching them to the top and bottom platforms. And if we look back here in Onshape, what I actually did is I designed these like snap-in ball sockets. So there's splits down the sides that allows the sides to expand out to let it snap in, and then they snap back in place to hold it in all tight. So back in the camera view, if I zoom in, which I think I can do, is that close? There we go. We can see I have the same splits here that I was talking about. And I can just snap these into place, just like this. Zoom back out so you guys can see the full picture. Oh, oh no. Well, we've certainly just learned something. Ball joint, or however this design worked, it split right at the layer lines here. That's okay for now. I think we'll rebuild these. I'm just going to redesign this anyways. You see on the bottom half, I did half splits instead of full splits. It seems to be a little more structural as it didn't just snap like these ones did. That's okay though. No big deal. Maybe the real answer here is don't drop it. Or I just need to give it a little more clearance. But in terms of manufacturability and how hard it is to build this, it's really not too bad. These ball socket joints are a little bit sketchy, just pushing them in because they're just 3D printed. Not my favorite feeling because it feels like I'm about to snap it every time I do it. I'm just going for like a slow, smooth push. And I still snapped it. That's cool. But, you know, it's just information for the next revision, certainly. And this side facing down. there it is, assembled. Now, ideally, this just as it stands would be pretty rigid, but I think because of that rotation I talked about earlier, we get a lot of movement that's pretty undesirable. Let me show you what I'm talking about. Here in OnShape, I mentioned that these actuators can spin along their own axes. So they can spin like this. And I believe that's what's causing all of this movement here. Stuff like this movement is all caused by it rotating around that axis. And if we zoom in and get close on one of the actuation points, ooh, way close. If I bring it in close to just one of these points and I hold it down, you can see that as I move it, there's a lot of motion along the rotational axes. So I'm just spinning it and moving it as if it was, which it shouldn't be able to do. A storage platform like this should be rigidly constrained where it is right here. But it looks like because there's so much movement in these ball joints, just like this, it's able to do a lot of movement that it shouldn't be able to do. So what could I do to fix this? What I'm thinking is in the next revision, what I'll have to do is, let me bring us back into OnShape here. If I do this one, yep. So if we look at this, instead of using ball joints, what I can use is some small universal joints here, or U-joints. And what a U-joint is it's basically just two, I really want off-road. It's just two normal pivots aligned so that their axes are perpendicular to each other and collide along a central point. And what this does is it still allows for the yaw, or it allows for the two axes of rotation we want, but it prevents that rotational motion we're seeing along the axes of the expansion of the linear actuator. So as far as that design goes, that's what we're going to have to do next to make this work. But for now, what I wanted to do, now that we have this assembled, is I want to talk about how I'm going to design a control board for this Yabbit animatronic here. So this V2 Yabbit animatronic with this as its main neck system. So this V2 Yabbit animatronic, what I'm going to do is I need a control board. So I'll open up KiCad real quick and start up a schematic and show you how I think through designing a schematic like that. So if I pull up KiCad, and open. Okay. So if I go to the Raspberry Pi Pico microcontroller GPIO, which is the microcontroller I really like using. If you've seen my other videos from all the tutorials I've done, all the way to all the tutorials I've done, as well as my latest project, they've all been heavily reliant on the Raspberry Pi Pico. And so will this project, which again, that's not what I want, which again is turning my old Yabbit animatronic into a much higher quality animatronic. And what I'll do is I actually want to put this on the trackless dark ride I've been talking about. So to synchronize that ride with the animatronic, what I'll use is I'll use like a Raspberry Pi Pico W, a wireless. My ride already heavily relies on Wi-Fi as communication between the control station, my laptop, my tablet, and the actual ride vehicle itself. So adding this animatronic on into that Wi-Fi network isn't that hard. It's actually pretty simple. So I'll use that to synchronize the motion, and then this Raspberry Pi Pico will control the animation. But again, looking at this output, or this pinout, what I need to do is I need to select which pins I'm going to put the put the servos on. Now, one thing I know I'm probably going to need is GPIO open available for the laser gun on the ride, as well as enough to control enough PWM to control all the servos and the LEDs inside of the eyes. If you remember in the Yabbit video, these eyeballs actually have RGB LEDs in them, and these are just ping pong balls, so they can glow basically any color I want them to, which can also convey a lot of emotion, given that I don't have pupils on this animatronic that can move around. So I'm thinking I'll use I guess what we'll really have to do is write out everything that this animatronic will have, which is let's see, if I open up Google Sheets real quick. So the Raspberry, or the animatronic, let's call it animatronic motion, it's going to have the STEWART platform, which requires 6 PWM outputs, 1 for each servo. And then I'm going to need eyes, which requires 3 PWM outputs, 1 for red, 1 for green, and 1 for blue. And by using 1 RGB LED in each eye, it's actually able to create any color the same way your monitor or your phone does. RGB, when combined, can create any color we want, so that's pretty cool. And then the other actuation we'll want, let's add a blink function, just like the original, to close its eyelids, and that's 1 PWM output. So that's 10 PWM outputs. Let's look up Raspberry Pi Pico PWM. I bet, yeah, 8 slices, 8 PWM slices, each with 2 channels. So we have 6 PWM channels, so that's a total of 6 PWM movements we're allowed to have. That's one, and we're up to 10 already. So we have 6 more available to us. And for now, I'm thinking that's all we're going to need. The only additional one I could see needing in the future is going to be like a wing actuator. Which is just one PWM servo, just like any other servo. And on the original Yavit, that's what these are right here. These are originally went through these slits in the outer skin casing and attached to wings. Because I was young, I just hot glued some plastic to aluminum, and the hot glue fell right off the aluminum. Well, actually, this side still has its wing here. We still have a wing here, and you can see it was able to flap its wing like this, which is pretty cool. And that might be something I want to add again in the future. But for now, this is pretty easy to do. The only other considerations for something like this is, what other things do we need to leave open? Ideally, we leave open like the SPI bus, and there's a lot of options to do that, so I don't think that's any issue. And the reason I want something like that is later I might want to integrate like CAN bus into the animatronic, just like on my ride. If I somehow end up doing it wired, or if I end up having like a full scene that has multiple animatronics, I can communicate between all the animatronics through CAN bus and devote one as the master. So the Wi-Fi network will only need to tell the master, start the show scene, and it communicates with all the other animatronics or special effects through that CAN bus, and the whole thing plays in synchronicity, which could be pretty cool. So I'll leave at least one of the SPIs open, and I'll actually refer to one of these, and this here is the schematic I have for the brushed motor controllers on the ride. So the controllers that control the big motors that spin the wheels on the dark ride. And you can see I here have the wiring to connect one of these CAN buses. See, I labeled it CAN there. I'm hoping that shows up through stream quality. Let's see, it's labeled CAN 1. And that's connected to the Pico there. That's pretty cool. So with that, I know what wiring I need to have. So I'll basically just need to leave this whole side here. I need to leave this whole side here open for the CAN bus expansion in the future. But otherwise, I have a lot of space available. Basically, these entire 20 pins for using as PWM outputs for the animation elements like the servos and the LEDs. In fact, I might be able to do something a little cooler. And since I have so many PWMs open still, 6, 9, 10, 11, what I can actually do is have each eye controlled individually, so that it can display a little more weirdness, a little more quirkiness through those eye colors. Because each eye will be able to control its color individually, it can act a little weirder. Yeah, that sounds good. So that's 6, 6, 6, 6. Okay. Cool, cool. Yeah. So, in just a second, what we'll do is, I don't think I actually have KiCad downloaded on my Windows install here, which is a little bit silly of me. What I actually have KiCad on is I have it on my dual boot Linux install. But what we can do is, it's a simple enough circuit that I can basically just start soldering. There's nothing all too complicated about this system. Yeah. Let's see. If I do this and then I check, just making absolute sure I don't have KiCad. Download. Yeah. Yeah. So what I'm gonna do is, I can very quickly just lay out what GPIOs I want to use with each of the what GPIOs I want to use for each of the animatronic animation elements, and then I can start soldering this. This really isn't that complicated of a circuit, so I'm not gonna bother trying to install KiCad on screen or anything. So lay it out like this. Yeah. Thank you, Grandma, but I don't actually think I need a new printer. Mine's going strong. I really like it. It's just that one type of plastic that I mentioned, the ASA. ASA is really hard to print in general, and even before I bought it, I knew it would be pretty hard to to print with my Ender 3. So I didn't have high expectations from the start, so I wasn't disappointed when it didn't work that well. I've actually all the way used up that whole spool back to PTG, which prints a lot nicer. It's a lot easier to use and comes out a lot nicer. That's the black material that I was showing earlier that came out a lot better. Here, let me move this to this side. Let's see. So I'm kind of thinking I'm just going to work my way down the list here and say that the Stork platform gets the GP0, GP1, GP2, GP3, GP4, and GP5. The only other consideration is these slices, the way the Pico works, it's split into 2 slices. It's split into 8 slices, and each slice has 2 channels on it. So that's what these numbers represent here. Like here it says PWM-A channel 0, PWM-B channel 0, or slice 0 channel A, slice 0 channel A, slice 1 channel A, slice 1 channel B. And the way that works is the PWMs are controlled individually, but the frequency is the same. So you can have differently widthed you can control the width of the modulation, like in the name, the pulsed width modulation, but the frequency of any two channels on the same slice are always the same. So what I want to do is I want to use the servos. The servos always need a frequency, specified frequency. It's pretty low. I think it's only like 60 hertz, 50 hertz. I don't remember off the top of my head, but I do know I definitely set it during my Raspberry Pi Pico servo tutorial a few years ago. So so what I want to do is I want to keep all the servos, all the motors, on the same PWM slices. That way they're all in the same low frequency PWM. And then the two LEDs, or I guess 6 LEDs, the two RGB LEDs, on their own slices. That way they can be a much higher frequency so it doesn't look flashy in the human's eyes or on camera. Because if you use low frequency PWM on an LED, it actually, you can see the flashes, or a camera can pick up the flashes, and that can create a really bad experience. So I'm on GP5, which means I've used channels 0, 1, and 2, or slices 0, 1, and 2 for the sort platform. And then I'll use channel 3 for the blink and wing actuator. So I'll call this GP6 and GP7. And then for the lights, we'll do 8, 9, 10, 11, 12, and 13. So channels 4 through 6. So I'll do GP8, GP9, GP10, GP11, and GP12, and GP13. Yeah, this setup looks pretty good to me. I don't need, I've got a good layout here for the servos, and then this way I'm up to 14 and up to here. All these pins that I'm circling here with my mouse will use for the animation elements, and then for the laser gun elements, because this ride has a laser gun, I need some way to install the targets, and for that I think I can use GPIO pin 14, 15, 21, 22 based on this schematic here. Let me do laptop webcam. Because those are the pins that are not used up by any of the animation elements or by the future CAN bus expansion. So what I will do is use 14 and 15 for those laser tag target electronics. What I'm assuming, or not what I'm assuming, but what I plan to do is to have one target in the head, probably between the eyes of Yabbit, and then one target in the body. That way there's no way you hit him in the body and you're like, why didn't that trigger? Well, it's because there wasn't a target there. But I'll include 2 targets in the ride, and that way maybe I can give more points for headshots too. So that could be a pretty cool element as well. So I'll say GP14 and GP15. Oops. GP15. We'll call these the target pins. Yeah. I'm just looking up on my board to see if I have a printout of the target I designed earlier. I don't think I do because it's all saved in my Linux OS that I was mentioning earlier. But that's okay. That is no big deal. You can always work around that. Let's see. Okay. Do online schematic editor. Yeah. Alright, let's see if we can just make a quick little demo. Yeah. That's not gonna work. Okay. Let me bust out all of my soldering stuff and we can start kind of building one of these, building a control board for this. Let's see. Going to need So, hi Grandpa, how's it going? So what I'm going to do is I'm going to solder this up on one of these. This is called a Vero board or a perf board, or according to China, a double-sided PCB kit. Basically what these are is they're just like fiberglass PCBs with a bunch of holes drilled in them, and then each of those holes is filled in with a bit of copper. So it makes it super easy to solder up a prototype board, or a control board in my case. Let's see. So I'm thinking I don't quite need the full size. This one might be adequate. Let's see how well this fits. Yeah, I'm thinking this one smaller size should fit. I can put the Raspberry Pi Pico all the way to one side. And I soldered that on using some of this female pin header. So the Raspberry Pi Pico goes into the pin header. Then that goes into the Vero board. And then on the other side, where I have all of the pins, where I have all this open space, this is where the pins for the servos will go, as well as the controller for the, as well as all the additional electronics for the target sensors, because those do require a little bit of extra electronics. So I'll try to leave about half the space for that, and the other half I'll use up here for the screw terminals for the power for the servos, as well as the actual pin headers for the servos, and as well for the LEDs. Let's see. So let us start just by soldering on the PCB then, on this Raspberry Pi. So what I'll do is I will pull out the trick to cutting these female pin headers. For the male pin headers, it's pretty easy. All you do is you get your flush cuts and you go right between two pins, and you can just cut and it'll snap right apart. That's not going to focus there, but that's okay. For the female pin headers, what you actually have to do is you pull out one of these spines, which I will show you right here. You pull out one of the spines, just like that. See, it's just a little like fork looking piece. And then on the spine you just took out, you take your flush cuts and you just basically crack the plastic, and you end up with two halves. Then with these Raspberry Pis, one of the things I'm thinking about is I need to maximize space on this side of the PCB for all the other electronics, but I also need a way and a space to run wires to the pins on this side of the Raspberry Pi. In fact, I'm almost thinking it would be better to do it this way, because so many of the pins we talked about using are on this side of the Raspberry Pi Pico. Yeah, this looks better to me. And then the other side is still accessible because I can run wire around this side and down in through between the Raspberry Pi and the breadboard and reach these other pins. Or I can solder wires on the underside, which also allows me to just pop over and go right to where I need to be. So yeah, I'm liking this a lot. Let's solder this into place now. So if while I'm soldering, feel free to ask any questions you have about projects or anything you would like to see in the future, or even if you just want to comment about how questionable my soldering is. Let's see if I can get you a little closer view of this. There we go. That's a little better. Feel free to drop any questions you have in the chat. I'll be glad to answer them while I solder. The trick to soldering lots of little pins like these, I found that the highest heat my solder iron goes, 400C, works well. Additionally, what you want to do is you just want to touch it just slightly, and then you don't want to put your solder to the soldering iron because what just happened there happens. What happened is the solder all went straight to the iron and not to the actual pin, which isn't good because then you're not soldering anything, you're just kind of wasting solder. So you want to touch the solder to the pin itself. You want to get the pin nice and hot, then melt the solder straight to the pin. That way the flux core gets all up in that pin and the solder does the rest of the work. It's pretty easy. You just have to keep going. You get pretty good at it pretty fast because you just have to do it so much. Like even for this Raspberry Pi Pico, there's 40 solder joints. 40 solder joints on this back side soldering the female pin header, and there was 40 solder points on this side soldering the male pin header to the Raspberry Pi Pico itself. And that is really hot. I shouldn't have touched that. Cool. So there's those 40 joints soldered on. So that's the Raspberry Pi Pico firmly mounted. Just like this. It's on there good. And of course it is removable. I just have to wiggle it out a little bit. That'll make it easier for soldering. Plus I can reuse the Pico I do end up using. This one went bad at some point. That's why I wrote bad on it. So I like to use this one for soldering because I know I can't break it any further than it already is. Which is always a good sign. Always makes you feel a little bit better when you know you can't break it beyond how far you've broken already. Now one thing I am going to add is this diode right here from this other schematic. This diode allows me to use an external power supply through the screw terminals I'm about to solder on, as well as plugging it in via USB. If I didn't have a diode there, it would effectively short the USB 5 volt power with the power from whatever power supply I'm using to power the servos, which at worst, or at best, blows up the Pico, and at worst blows up whatever laptop I'm plugging it into, which is no good at all. In fact, that'd be really bad. So what I'm going to do is I'm going to solder in that diode right here, and then I'll solder in some Raspberry Pi, or then I'll solder some screw terminals in for the power. Then I'll solder in terminals for the 8 servos that I'm talked about, and for the 2 RGB LEDs. Let me go grab those screw terminals. One of the joys of buying from China is that you end up with bags of lots and lots of screw terminals. I only need a few of these realistically, but I think I have 50 here. And I've used like 4 or 5 tops in the past year I've had this bag. But I'm going to take one of these 2-pin, 2-terminal one of these 2-terminal screw blocks and solder it in right about here for the power. Just to get the overall layout of the board, the screw terminals will go here for power, and then I'm going to need 8 3-wide male pin headers sticking out of the board, and that allows me to 1, 2, 3, 4, 5, 6, 7. Ooh, one short. But what this allows me to do is I can just plug the this is one of the wires off the servos. I can just plug that right in, just like this. It's super easy, and if that was soldered on, it'd be a super strong connection. Let me get a little more male pin header. So here we go. And then for the RGB LEDs, I'm going to use these 4-wide dew point connectors, or connectors, and that will allow me to have 1 pin for each of the 3. Oh, where am I? 1 pin for each of the 3 colors, and then 1 pin for a ground to that LED. So let's do it just like this. Yep. So you'll imagine big row of pin headers here, and then we'll have the big row of pin headers, big row of servo headers. Or if I can do it like this. The reason I want to lay up the board like this before I solder anything is because I really want to know that A, I'll have space, and B, I would really like to know the I'd really like to make sure I have I guess the same thing, but I really want to have space for the target electronics that control the target. And those I think will fit right in here because it's only a few resistors really that are needed. So I think this looks pretty good. I do want to move all of these up one though, just to make a little more space. These all look good. I think I'm ready to start soldering some of it in. So I'll start with the screw terminals because those are the easiest for me. Gotta wait for my soldering iron to reheat because this is it's a nice soldering iron. It heats up super quick. And one of the safety elements is that if you leave it just sitting for long enough, it turns itself off, which is a great feature. Prevents excessive power use. It prevents damage from overheating itself. The only thing is you do have to wait for it from time to time to turn back on, which that's a more than willing sacrifice. That is super convenient overall. I think here looks good for this one. With these, I actually do need to install 3 resistors per RGB LED, so I'm trying to leave space for those right through here. So that's going to be a total of 6 resistors. I believe there's plenty of space for that right through here. And then the servos don't need any resistors or anything, so there's not going to be any space left for them. Now, let me grab those resistors just to make sure we have space. Another one of the joys of Chinese electronics is a giant box of resistors like this. I'm never worried about running out of resistors again. Or I suppose I am worried I'm going to run out of all the ones I need the most. And then have a bunch of random values that I never use, which I suspect is what is going to happen here. What I'm looking for is 220 ohm resistors. Based on the LED I have here, as well as the voltage output from the Raspberry Pi Pico, 220 ohm is the right amount, and I just found them here. Cool. So I'll need 6 of these 220s. One, two, three, four, five, six. See, what pins did I say? Referring back to the spreadsheet I made, I would like to use GP 8, 9, 10, 11, 12, and 13 for the LEDs. which means 8, 9, 10, 11, 12, 13 is pin 11, 12, 14, 15, 16, 17. So let's use pins 20, 20, 19, 18, 17. So what I'm thinking is I'll use these resistors just straight out of the Pico. And I'll show you what I mean here in a second. I'll use the resistors just straight out of the Pico like this. Oh boy. So I'll lay it out so the resistors come straight out of the Pico. And on the back side, one of the legs goes straight to the pin it's going to work with. And then this other side can have a wire that goes to the pin header. Before I solder, I want to talk about I want to spend a little bit of time before I solder the rest of this to talk about how I plan on animating the animatronic. The animatronic is actually one of the things I really want to do with this animatronic is integrate it into my ride. And to give you a sneak preview, just a little bit of my next video that's coming out, hopefully by Friday, is I've made the ride trackless, and then I'm using Blender to animate that the profile that the ride takes. And what I'd like to do is be able to make a video, not a video, but make an animation or make a 3D model of this animatronic in Blender that I can then animate in Blender. And by doing that, I'll be able to export that animation directly from Blender and play it on the Raspberry Pi Pico. Now, the interesting thing is, since the ride's already going to be animated in Blender, I'll be able to animate the Yabbit in the same Blender file so it's synchronized with the ride's motion, and I'll be able to put a camera on the ride vehicle in Blender so I can get a visualization of what the ride will look like with the animatronic before I even build it. So that could be a pretty cool system because I'll have that pre-visualization. I won't need to be constantly exporting to the animatronic, watching it. It will take out a lot of steps. Additionally, the other cool thing about it is by doing it this way, I can have any number of animatronics all synchronized with the ride, all synchronized with the ride, and I won't have that huge nightmare of does this animation on this animatronic look good compared to this one next to it. Because I'll be able to animate them all in the same Blender file and export them all as separate CSVs, and export the animation separately to each animatronic, but still know they'll be synchronized together because they were animated right next to them in 3D, which will be a really cool effect. So that's one thing. Probably in the next few streams, I'm thinking I'm going to keep streaming every week, same time on Tuesdays. So in the next few streams, we'll keep working on this animatronic. Next week we'll probably utilize the U-joints, like I mentioned in a previous earlier, because those ball joints in the socket aren't super effective. There's a lot of motion that there shouldn't be. As well as we can design further what we're going to want to do. So just like this, I'll replace these ball sockets with U-joints. Hopefully it doesn't require too much rework of the design. Honestly, it might actually only need one side to be U-joints. Because if only the bottom is a U-joint, it's still constrained axially then. So there won't be that rotational motion, and the top side can still be the simpler to construct ball joints. My only worry then is that the ball joints are pretty fragile. I think I broke almost all of them just assembling them now. So that won't be too hard. It might even be better to put U-joints on both sides. I'll just need to come up with a way to 3D print them such that they don't need bearings in every single joint, because a U-joint could use up to 4 bearings, which would be way too much. Way too many bearings for this, because it has 12 U-joints times, that's 50 bearings, which is too much. It would get big and heavy really quick. So we'll work on that. The other thing we can do is we can start developing the rest of the animatronic around this storage platform, because we still need a head to go up here on top of the platform. We need the rest of the body to go around the lower of this platform. Yeah. We need the rest of the body. And a space to mount all the electronics and power supply. So that won't be too difficult, I'm thinking. Yeah. So with that, I think I've stalled enough while my camera charges a little bit, because I just killed it, let it die. Let me restart my camera and we can go back to soldering for just a few more minutes. I don't think it'll be too hard to finish up a little bit more soldering. At least we can get these resistors in. Here we go. That's the camera back online. At the minimum, we can get these resistors back in, which should be super easy to set up real quick. I'm going to get you mounted back on the tripod. just the last few resistors to solder on. In these last few minutes of the stream, I welcome everyone or anyone to ask any questions. Let me know of any ideas you have, any suggestions for the channel. I would love to hear everything you guys have to say. So feel free to let me know. Oops. Feel free to let me know of any suggestions you have, any questions. I'm more than willing to answer them in these last few minutes of the stream. I'm planning on ending right at 6:30, so a nice 2-hour stream to start off this streaming series. It's been super fun. I'd love for any feedback or concerns. Anything you guys want to say, I'd love to hear. Now, one of the a tip I have for soldering resistors on this is you see I've got them all lined up in a row next to the pins I want to connect, and then on the back side, what I do is I bend out the leads so that it basically holds itself in place. So while I'm soldering, it's super easy to just put a little solder joint on each of one of these points, and then it's in there permanent, and I can cut off the rest of the lead. Additionally, these leads help as a nice little way of connecting to the actual Raspberry Pi pins without having to make a giant solder joint. So I'll just get these soldered up real quick. These joints get really easy to do once you're used to it. You see how fast I'm moving along. It's just a quick little touch, solder, touch, solder, touch, solder. And just like that, in just those few minutes, I just did like 18 solder joints. Through hole soldering like this. It's super easy once you're used to it. And I just do a little visual inspection to make sure. See if I can get focus. I like to do a little visual inspection to make sure I haven't accidentally crossed any leads or not used enough solder anywhere. And to me, this solder joint is looking pretty good. I'm liking how this all turned out. So I'm going to cut these leads off here because I know that's as far as I need them to go. And then over here on the other side, I'm going to start soldering on these other wires, or these pin headers, I mean. And then, after that, I'll be able to solder some wire to each of the 3 pin positions, as well as for ground on these these pin headers for the LEDs. And then I'll be able to have plenty of space for the servos down lower here. In fact, I think there's so much space, I'm going to give myself a little extra leeway and make this a little wider, just to give myself some more space while I solder. because I have plenty of space here. I'm not too concerned how simple this design is. It's super easy. Let's see. I think a lot of the time soldering these, as well as soldering normal PCBs, is figuring out a good way to hold it. And I guess that's true of any manufacturing technique. It's always a question of how do I hold my piece. If you ever talk to a machinist, they love talking about how they hold, or how they design new clamps, or the clamping system of their machines. And it's the same here. I have to figure out the best way to hold this pin header while I solder it. One of the important things is I don't solder it too crooked, which as it is now, it is very crooked. But I think that right there is pretty good. That's looking good to me. And then what I'll do is I'll just solder one joint, only one of them. There we go. And that way, I'll take it out, and that one solder joint's plenty to hold it. And you see how it's a little bit crooked? See if we can focus. This pin header I just soldered is crooked. What I can do is I can loosen that one solder joint and hold it in place while it cools again. Since I only did the one, it's super easy to unsolder and resolder. And now it's sitting a lot straighter, which is a lot nicer to work with. And that solder joint holds it in place while I do the rest of the solder. There we go. Look at that, super duper easy. Very awesome. Alright, so I think that's going to have to do it for today. It was a super fun stream. Let's see what we got. We built this storage platform that we have here, or at least we assembled it. We discovered there's some error in my design here. Before the next time I stream, I'll have a U-joint design going, as well as the hexagonal design I talked about earlier. And just to remind you guys what that means, just like in the Wikipedia article for a storage platform, it's got this kind of joint where there's basically like a triangle where the 6 actuators connect, and the 2 actuators are right next to each other on the top and bottom, so it forms some nice diagonals that creates a lot more structural strength, as well as, I believe, probably going to add a lot more rigidity so it doesn't move around as much as mine does, as much as this first revision does. And then we started soldering up our control board here. It's super simple. Next time I'll make sure I'll have KiCad so that we can actually make a schematic, look at how all that works. It's pretty easy. I'm sure a lot of you will like it. So I'll leave a few minutes. If anyone has any questions, let me know. I'll be happy to answer them in these next few minutes, and then I'm going to end the stream. So I'll give you guys like 2 minutes tops. Any last questions, anything you want to say, I'd love to talk to you guys, so let me know. And for this one, I'm going to do the same thing, just do one solder joint. Take it out, see how straight it is. Fix it if I need to, which it looks like I do in this case. There we we go, nice and straight. And I can solder up the rest of them. Again, if you guys have any questions, let me know. I'll be glad to answer them right now before I end the stream. There we go, nice and clean solder joints. The last step to soldering is always to re-tin your soldering iron. Scrape it off real good. Tin. Thank you to everyone who joined me for this stream. I hope you guys learned a little bit about STEWART platforms or maybe electrical design or soldering. Thank you. Please join me again next week. We'll continue working on this project. We'll continue designing this animatronic, soldering up. We might even be able to start programming next week. So thank you again for joining. I'll see you guys next week.